streaming.
So the live streaming there is being managed by which app? Because you had a choice to live stream to Facebook and to live stream to YouTube.
Yeah.
So
the live streaming is being managed by ISOM, which then sends the stream to either of those. All it needs is for you to log in. Okay, so, and you can stream to both at the same time. That's pretty impressive. If you wanted to. You need to be honest. Sorry, see yourself.
Yeah, good.
Bosh.
All right. So let's see if we can get through this a bit quicker tonight and clean up a bit. Good. All right. Thanks, Tom. All right. So welcome to the live stream. This is the paper 2, the structured questions for AS level chemistry from 2016. Let's just scroll up. Okay. All right, so in this question, they're guiding you through step by step, and you're going to start off by calculating the amount in moles of hydrochloric acid. So you need to use the equation that you know that, well, I need a pen. You need to know that concentration is the amount divided by the volume. If you want to work out the amount, which is what they're asking for here, you've got to rearrange that equation. So the amount, N is equal to the concentration times the volume. So on this occasion, the concentration was 0.2 moles per decimeter cubed, and the volume was 30 centimeters cubed, and we just have to be dimensionally correct here. Because that concentration is in units of decimeters cubed. So we have to change it from centimeters cubed to decimeters cubed. We divide it by 1,000. We multiply all that together, and we end up with an amount of 6 times 10 to the minus 3 moles. Now, they're guiding us through step by step. So they're asking us next to write the equation for the reaction. That's GCSE knowledge. An acid and a base makes a salt and water. So we can just put in there the acid and the base, making a salt and water. Easy stuff. That's GCSE knowledge. And then next step is to calculate the amount of sodium hydroxide. Easy again. You can see there's a simple 1-to-1 stoichiometric ratio between the amount of hydrochloric acid and the amount of sodium hydroxide. We know the amount of hydrochloric acid, so we've got exactly the same amount of sodium hydroxide goes in there. All right, next step. We've got to calculate the amount in moles. So we know that initially, whoops, pen turned off, turn that on again. The amount, still pen turned off. The amount of sodium hydroxide initially was this. Again, sorry. Again, we're converting a volume in centimeters cubed to a volume in decimeters cubed. So we had that many moles of sodium hydroxide initially. And then we reacted, or we had that many moles left over. So if we started with that, and we had that amount left over at the end, then the amount that reacted was the difference between those two. So you've got 0.01 minus 0.006. Well, the amount there is the difference between those two, it's 4 times 10 to the minus 3 moles. Or if you wanted to put that, it's that, isn't it? Okay. So moving on to next question. we have to calculate the amount of moles that we had of this originally. Well, we know from the stoichiometric ratio, if you look back to the question, that you had 1 mole of that was giving you 4 moles of hydrochloric acid. So you've got a 1 to 4 stoichiometric ratio, and we just calculated just up here the amount of hydrochloric acid. Scroll down. The amount of hydrochloric acid was 0.004 moles. We calculated that just now. And because we've got this ratio, then the amount of this tetrachloride, of course, must be 0.001 moles. So the amount there is 0.001 moles. And then because we now know a mass and we know an amount, we should be able to work out the molar mass and the molecular mass. So you need to know that the amount is the mass divided by the molar mass. Rearrange that. So the molar mass is the subject to the equation, and that is the mass divided by the amount. The mass we had was 0.17 grams, and the amount that we had was 0.001. Divide those, and we get a molar mass of 170 grams per mole. And just to convert between a molar mass in units of grams per mole and the relative molecular mass, which is a unitless number, we just have the same numerical value. So the relative molecular mass there is 170. Final step, we've got to calculate the relative atomic mass of X. Well, we've got a little calculation here that we know we've got X, we don't know its relative atomic mass. We do know that we've got 4 chlorines, and we know that when we add all those together, we've got a relative molecular mass of 170. Well, we can look up the relative atomic mass for chlorine in the data book. We've got 4 of those. The relative atomic mass for chlorine is 35.5. We can have 4 of those, so that's 142. And so we just have to work out what this value is so that when added together, it gives us a relative molecular mass of 170. Do that, and you work out that the relative atomic mass of X that we need to add to 142 to make 170 is a relative atomic mass of 28. So the relative atomic mass of X is 28. And to look that up, to find out exactly what that is, you look that up in the periodic table. The element with the relative atomic mass of 28 that's in group 4 and forms a tetrachloride is silicon. Good, next question. So you've got to start off with explaining. This is one of your sort of key words, or one of the trigger words that you come across in exam. So we've got to explain the meaning of standard enthalpy change of combustion. So we don't want to just do the definition. We've got to have 3 points here. And 3 points that you're looking for is the enthalpy of combustion is you want to have that you've got complete combustion. My pen's not working very well. Complete combustion of 1 mole. In a lot of these standard enthalpy change definitions, you'll find that you're talking about 1 mole, and here we're talking about combusting 1 mole, but we're wanting to make sure that we're completely combusting it. So, for example, if you are combusting carbon, you'd make sure you are completely combusting carbon to CO2 and not incomplete combustion to carbon monoxide, for example. So we've got complete combustion of 1 mole of a substance. And then we need to say that this enthalpy change is being measured under standard conditions. And you should know those standard conditions are a pressure of 100 kilopascals and temperature of 298 K. These are the standard conditions. And that the reaction, the standard enthalpy change of combustion, is for the reactants and their products in their standard states. Okay, so we've got complete combustion of 1 mole of a substance under standard conditions with reactants and products in their standard states. We've made sure we've got our three marks there. Okay, so we've got to write this complete combustion of ethanol. Let's write that out. C2H5OH. Combustion, of course, we're making carbon dioxide and we're making water. It's complete combustion. We've got carbon dioxide, not carbon monoxide. And we've got complete combustion. We've got plenty of oxygen to make this happen. Do the stoichiometric coefficients. I'll do the hydrogens first. I'll do the carbons next. And to balance it all up, I need a stoichiometric coefficient of 3 for the oxygens. So we're now, we've got a definition up there, we've explained it, and then we've written the equation there, and now we're getting on to some practical work. You've got to calculate the enthalpy change when we're burning this amount of ethanol. You need to know that the heat is mass times the specific heat capacity, which has a symbol C, times the change in temperature. And the only thing you have to watch out here is that when you're measuring the amount of heat, you're measuring the temperature change in the water that's surrounding this calorimetry experiment. And so the mass is not the mass of ethanol, but it's the mass of water whose temperature has been raised. So that mass is the mass of water, not the mass of ethanol. And that's a kind of point that you have to watch out for in these kinds of questions. So specific heat capacity of water is given to you in the data book. You've given here the mass of water. We know that's 100 grams. And we've got a temperature change of 16.3 degrees Celsius. And a change in Celsius is exactly the same as a change in Kelvin. So even though this is expressed in Kelvin, 1 Kelvin is the same as 1 degree Celsius. So we can just plug these numbers in. So we've got a mass of water, that's 100 grams. You look up the specific heat capacity of water in the data book. That's 4.18. Oh, pen's lost again. And the temperature change in Kelvin is the same as the temperature change in degrees Celsius. So you're multiplying all those three together, and it gives you a heat of 6,813.4 joules. Okay, so we just, if you look up the units of the specific heat capacity, they're expressed in joules, grams, and Kelvin. So we're dimensionally correct here, and we've got a heat released of 6,813.4 joules. I'm losing my pen again. There you go. Good. Now, that amount of heat was released when we burned 2.3 grams of ethanol, and that's not a mole of ethanol, that's much less than a mole of ethanol. So this is the energy that's released when we burn less than a mole, and now it's asking us to calculate the enthalpy change when we burn 1 mole. So we started with 0.23 grams of ethanol. The molar mass of ethanol is 46 grams per mole. So to go from mass to 1 mole, then you can see that the amount is the mass divided by the molar mass. So if we divide this by the molar mass, then we find out that we've got 0.005 moles of ethanol. But we don't want to know the amount of heat from 0.05 moles. We want to know the amount of heat that will be released if you burn 1 mole. So we've got that amount for 0.005 moles. To get the amount for 1 mole, we take that and divide it by the number of moles. So you're taking 6,813.4 and you divide it by 0.005 moles to give you the amount of heat from 1 mole. And what you get is a large number, and you have to divide it by 1,000 because we're moving from joules to kilojoules, and the value that you get there is 1,362 kilojoules. We divided by 1,000 to get that in there. And it says here, just check the question again, we've got to include a sign in our answer. Well, was heat taken in or given out? It was given out in this because we measured the temperature of the water and how that increased. So the heat is being given out. That's an exothermic reaction. Exothermic reactions, by convention, have a negative sign in front of the numbers there. So the enthalpy change is minus 1,362 kilojoules per mole. So that's the value that we determined. But this enthalpy change might be less than the true value. Now, why is that? Well, the classic answer, okay, we've got to get 2 points here, haven't we? The classic, one of the classic reasons for that, of course, is that some of the heat from the burning escaped from the apparatus. I'm losing my pen here. So some of the heat escaped and wasn't captured by raising the temperature of the water. So that's a kind of obvious one, that not all the heat was captured to raise the temperature of the water. Some of the heat escaped. And then because we've got to get 2 points here, we've got to think of some other reasons why this isn't the same as the true value. Other reasons could be, well, as we said right at the start, this enthalpy change of combustion is for complete combustion of ethanol. Now, maybe we had an experiment where there was, oh, I've lost the pen again, incomplete combustion. And because the standard enthalpy change of combustion requires complete combustion, if we have incomplete combustion, then the value that we determine would be less than the true value. You could say some other things like, well, we thought we had, 0.23 grams of ethanol. Ethanol happens to be an extremely volatile substance. It's very easy for it to evaporate. So maybe even though we had 0.23 before we could sort of complete the experiment, some of the ethanol had evaporated. So perhaps we didn't really have 0.23 grams of ethanol. So you could say that ethanol is volatile, meaning it evaporates easily. It's a low boiling point. And so we didn't have as much ethanol as we expected to. And finally, and this is a little bit esoteric, is that these kinds of experiments should be carried out at a constant volume. And if it's not carried out at a constant volume, then some of the energy that we should have captured is used to expand, to push back against the atmosphere. That's so-called work done. So if this experiment wasn't carried out at a constant volume and some of the energy was used to expand against the atmosphere, then we haven't got as much of the energy transferred as heat because we used up some of the energy to expand against the atmosphere. So you've got the obvious reason, well, we lost some heat in the experiment because some heat was lost from the apparatus. And then you've got some of these other reasons why your true value, the value that you determined, is not the same as the true value. Okay, next one. Okay, so you've got to create a labeled energy cycle, and you're trying to calculate the energy of formation of propanol here from these enthalpies of combustion. And so what you're looking for there is an application of Hess's law that basically says, well, it doesn't really matter which route you use. You can have one step, you can have two steps. As long as the starting conditions and the end conditions are the same, then the enthalpy change is the same whichever route you take. So we're trying to find the enthalpy change on this route here. We don't know what it is, but if we can find another route that gets from the same starting place to the same ending place, then the enthalpy change on that route will be the same as this single step up here. All right, so you've got enthalpy changes of combustion given to you up here. So if we do a combustion here, well, if you completely combust carbon, you're going to end up with 3 molecules of carbon dioxide. And because the enthalpy change of combustion is just per 1 mole, then this is per 1 mole of carbon, but we've actually got 3 moles of carbon here. So we've got to have 3 times minus 393, haven't we, to go there. Okay, so we've done the carbon dioxide, and then we're combusting the hydrogen. And when we combust hydrogen, then we get 4 lots of water. Yes? And because, again, the enthalpy of combustion of hydrogen is for 1 mole of hydrogen, here you can see we've got 4 moles of hydrogen. So we've got to have 4 times minus 285.8. Okay? And that gives us all of this. And so we've got that step there. And we've got the enthalpy of combustion of propanol over here. So that's giving us, if you completely burn propanol, you end up with this amount of carbon dioxide and this amount of water. But because we've got the enthalpy of combustion here for propanol, we don't need to multiply up by anything here because the enthalpy of combustion is for 1 mole of the substance. We've just got a stoichiometric coefficient there implicit of 1. So that is 2021.0. All right? So for Hess's law then, we're trying to find that value there, aren't we? Now, so if we say we've got that enthalpy change there, which is delta H1, that enthalpy change there, which is delta H2, and that enthalpy change there, which is delta H3. And the way we've drawn it here is, well, you could go 1 step, 2 steps, or you could go in 1 step. You can see that gets us to the same place. And Hess's law is saying it doesn't matter which route we take, as long as we start from the same place and end in the same place, then the enthalpy change is the same. So that means that delta H1 plus delta H3, so that step plus that step equals that step there, doesn't it? Which is our delta H2. But we are trying to find this, aren't we? Delta H1. So we've got to make that the subject to the equation. So delta H1, which is the thing that we're trying to find out, is equal to delta H2 minus delta H3. Okay, and if we plug all the numbers in now, we'll work out what delta H1 is. Delta H2 is all of those added together. And delta H3 is that, but we're going to have to take that negative sign and change it to a positive sign because we've got minus times a minus there. And if you plug all the numbers in, you end up with the enthalpy change of 302.7. And actually, when you plug the numbers in, you end up with a negative number, which is what we'd expect. You need to check back there. Well, if you're well, there's no reason for us to particularly expect exothermic or endothermic. So you end up here with an exothermic reaction that the enthalpy change of formation for propanol here is negative. Okay, next question. Okay, we've got a couple of lines here, and we've got to show that, we've got to explain why both lines are showing an increase in radii as you go down, and this is group 2, isn't it? Group 2. And it's telling us that we've got atomic radii and ionic radii. So two different types of a radius. So, why are those radiuses both getting larger as you go down the group? You've got to have two points here. First point, as you go down the group, then you're going, for each step down the group, you're going to a new period. And so you've got an increase in the number of electron shells as you go down, step down through each member of the group. And the second point is that as you go down the group, you're increasing these electron shells, but at the same time, you're increasing the nuclear charge. But because you have more and more of these electron shells, then the outer electrons are more effectively shielded from the increase in nuclear charge. So even though you might think that these electrons are being drawn in closer because the nuclear charge is increasing, actually these radii are increasing because you've got new shells of electrons that is effectively stopping the full nuclear charge being experienced by the electrons on the outer shells. So the outer electrons are effectively shielded from the increase in nuclear charge. And so we've got two reasons there why these atomic and ionic radiuses, or radii, are increasing as you go down group 2. Okay, so next question. You can see your trigger words or your keywords here. You've got to state and explain. So you can understand how you're going to get 2 points there, one for just saying something and 1 point for explaining about it. And you've got to explain which line is the atomic and which is the ionic radii. So just state that the top line is the atomic radii. And now that you've stated it there, and now you've got to explain it in part 2, and you can explain it by saying that in group 2, if you have a group 2 element, its ion is 2+. And so electrons have been removed, and so the ion has one less shell than the atom. And that's the reason that the atomic radius is larger than the ionic radius, because in the ion, electrons have been removed, and so the ion has one less shell than the atom, and so it's smaller. Good. So continuing to test your group 2 knowledge here. We've got a salt of a group 2 element, and when we heat the salt, we get a brown gas. Pen's gone again. Just click that back on. Okay, so when we heat this salt, we get a brown gas, and probably the only brown gas you're familiar with at the moment is nitrogen dioxide. So that's giving us some clues there. White solid remains. So this should be flagging up in our minds because we've studied the thermal decomposition of magnesium nitrate. And when that is heated, then you end up with magnesium oxide. That's a white oxide. You end up with nitrogen dioxide gas, and you end up with oxygen as well, actually. And so that's the balanced equation for that. So that's just something that you've learned. I mean, we don't actually know that this is magnesium nitrate. We don't know that yet. But at the moment, it's asking us is to ask us what the anion is. Remember, an anion is negatively charged. Mg2+ is the cation. And so the anion in this salt is going to be the nitrate. And the nitrate, you can see, because, for example, magnesium nitrate is Mg, that's Mg2+, isn't it? So the nitrate as an anion must have a single negative charge. That's the nitrate. So you can just say the anion is the nitrate. Now, you've got to look back in the question here, and it's telling you that after you've heated this group 2 nitrate, the solid then dissolves to form a colorless solution of the metal hydroxide. And you need to know that as you go down group 2, the hydroxides become more soluble. All right? So if this metal hydroxide dissolves in water, you can see there it's a colorless solution, then it must be at the bottom of group 2, not the top, because the hydroxides are more soluble at the bottom of group 2. And later on, they're adding a sulfuric acid, and that colorless solution, this magnesium, or whatever this hydroxide is, forms an insoluble precipitate. So that's a clue that with sulfuric acid, you're forming a sulfate. And you need to know in group 2 that the sulfates have the opposite behavior. So the sulfates are more soluble at the top of group 2. All right? So you've got something here which is soluble for the hydroxide, but insoluble for the sulfate. And that must mean it's at the bottom of group 2. And so we come to this question over here. You've got to identify the element M. Well, you've got to pick something that is at the bottom of group 2. And a good one to pick is barium. Pen's lost again. Ba. Because you should know that barium sulfate is insoluble. All right? So you've got to write an equation then for the formation of barium sulfate. It's an ionic equation, so we're going to miss out the spectator ions and just include the ions that are reacting here. And we had the barium ions. We know it's group 2, and we know when we started off that they were in solution. Yes? And we're reacting it with sulfate anions. They're in solution as well. And when those two react together, then we form the precipitate barium sulfate. So we put a state symbol there, it's a sulfate, and you can draw a line going down to indicate that's a precipitate. So we've got an ionic equation there because we've left out the spectator ions and just included the ions of interest, the ones that are going to form the precipitate. Okay, so that means we're just left with trying to figure out what the salt was at the beginning. We know that the anion was the nitrate. We had that earlier on. And we know that the cation, because we've just been through it here, is barium 2+. Okay, so to form, sorry, that's an A in there, isn't it? So to form the formula of the salt, Well, that's going to be Ba, and we've got to have 2 of the nitrate anions to balance the 2 positive charge on the barium cation. And the overall equation for that, well, we've got the barium nitrate, and we're heating it, and we know that it formed nitrogen dioxide. We have a white solid, barium oxide, and actually you get a mixture of gases, you get oxygen as well. So you've got the reactants, the products there. You just have to work through the stoichiometry. You end up with 2 of those, and 4 of those, and you can check that those all balance up. You have the same number of each kind of atom on both sides of the equation. Those are our 2 marks. Okay, we're still talking about group 2 elements here. Again, we're still being asked for ionic equations, and we're talking about calcium carbonate and calcium hydroxide. And it's talking about the ionic equations for the neutralization of acid by the hydroxide and the carbonate. Well, for the hydroxide, we just put in the ion of interest, which is the hydroxide ion, and we can have that the states again, and we've got the hydrogen ion from the acid, and when hydroxide from calcium hydroxide is neutralizing the hydrogen ion from the acid. Remember, we've just missed out the spectator ions, we're just putting the ions of interest, then those 2 just make water state symbol as a liquid. Similar kind of thing for calcium carbonate. The anion of interest is the carbonate anion, and we're reacting that with acid again. Put our state symbols in, and this is GCSE knowledge. When you react a carbonate with an acid, you end up with a salt. We're not drawing that in because we're just doing the ionic equation. You end up with carbon dioxide and water. And to balance that up, we need 2 of those. So we've got the ionic equations there. And then again, you've got your keywords here. You've got to suggest and explain. You've got to go for 2 marks here. Why calcium carbonate is a better choice for neutralizing acid than calcium hydroxide in areas of high rainfall. So suggestion, that's your first mark, isn't it? If you remember, as you go up to the top of group 2, then the hydroxides are becoming less soluble. Calcium is not right at the top of group 2. So calcium hydroxide will actually be soluble to some extent, and you should know that from GCSE work, because a solution of calcium hydroxide is lime water. You've used that for doing some tests in GCSE. So we know that calcium hydroxide is actually soluble in water. And so the reason we don't use calcium hydroxide is because in areas of high rainfall, it might dissolve up and be washed away. And we're going to explain that by saying that calcium hydroxide is more soluble and gets washed away than calcium carbonate, which is insoluble. So calcium hydroxide is more soluble than calcium carbonate. And so the calcium hydroxide will be washed away, calcium carbonate wouldn't be washed away. We've suggested a reason and given our explanation 2 marks. Okay, finally, this is just testing kind of recall. You've got to know the reaction between magnesium metal with cold water and magnesium metal with steam. So first one, this is in cold water. You get magnesium hydroxide, 2 of those, plus hydrogen. But they're only, I haven't balanced the equation, they're just asking for the formula of the product when magnesium reacts with cold water, and when you've got steam, then the reaction is a bit different. You end up with magnesium oxide and hydrogen. But again, they're not asking for the balanced equation, they're just asking for the magnesium-containing product that's formed. You've got your 2 marks there. Okay, moving on. This one, scrolling up. All right, moved on to question 4. We're now being asked a question about stereoisomerism. And you should know 2 types of stereoisomerism. One is so-called EZ isomers. Come on to those in a moment. And the other type is optical isomerism. So stereoisomerism is when you have 2 organic compounds. Oh, sorry, one organic compound that has the same molecular formula, but has different arrangement of its groups in 3 dimensions in space. So you're looking for a definition there of stereoisomerism, and you're going to say stereoisomerism is when molecules have, I've lost it here, have the same molecular formula, but, and this is where the isomers come in, different arrangements of atoms in space, or you could say different spatial arrangements of atoms and groups. So there's this organic compound up here. It has 1 molecular formula, 1 structural formula, but it can have different arrangements of those atoms and groups in 3 dimensions. And because it can have different arrangements of those atoms and groups, that's another way of saying it shows stereoisomerism. Now, we've got to then figure out how many stereoisomers there actually are. That's the next question down here. So, well, if you look at this compound here, you've got this double bond. And you need to remember that when you get a double bond, that means that the group on this side of the double bond and on this side of the double bond can't rotate around that double bond. They're kind of stuck in position. And because they're stuck in position, they could be stuck in one position or another position, and so you end up with 2 stereoisomers. So if you've got the double bond and you've got the carbon atom on this side and the carbon atoms on this side, you can end up with a group there and a group there, or you can end up with the group stuck up there and the other group stuck up there, and they're distinct because this double bond can't rotate. You end up with that kind of isomer where the groups are on sort of opposite sides of the double bond, or they're on the same side. And that kind of isomerism is called, we had it up there, EZ. This is the E form, and this is the Z form. Okay, and so this organic compound up here could have 2 isomers which have either the groups like this, or on the same side of the double bond like that. So we've got at least 2 stereoisomers because we've got E and Z isomers of the compound there. But the other kind of stereoisomer, along with these EZ isomers, are the optical isomers. And the optical isomers happen when you've got 1 carbon atom and it has 4 different groups or atoms around it. And that gives you an optical isomer. So you need to look at this and see if there's anywhere in that molecule that has a carbon atom with 4 different groups around it. And if you're looking carefully, you've got this one here. If you just try and draw that out, you've got that carbon atom, and it's got a hydrogen atom, you can see that, and then it's got this C2H5 group on one side, and then it's got a methyl group off there, and then it's got the rest of the compound over there. So that's definitely, it's called a chiral carbon. It's and when you have a chiral carbon, then you have 2 optical isomers. So we've got 2 isomers from this isomerism, they're EZ isomers, and you've got 2 optical isomers. So altogether, you've got 4 stereoisomers from this compound here. Okay, good. So now they're testing you on your ability to name organic compounds. So you've got to figure out the name here. If I can just find a bit of space to work on that. So if you drew that out, I've lost the pen again. Get that. So this is now the fully displayed formula. So you've got that. And then you've got these 2 methyl groups at each end. That's the fully displayed formula. And you've got to name that. So the rules for that is that you first have to work out the longest chain. And that's going to give you the so-called stem. Oh, I can't write that. The stem for the name of that organic compound. So if you look for the longest chain of carbon atoms, well, there's a number of ways you could draw it. They're all the same, actually, and you're going from 1, 2, 3, 4. So when you've got 4 as the longest chain of carbon atoms, the stem for 4 is bute. The stem for 3 is prop, the stem for 2 is eth, and so on. So that's the first thing. You look at the stem, you've got 4 carbon atoms. The next thing you look at is the functional group. Okay, you can see here, well, there's not much going on except for that double bond in there. So the interesting part of this molecule, the functional group that we're interested in, is going to be the suffix. We had the stem before, now we've got the suffix, and so the suffix is -ene. And then we've got to work out exactly where that -ene is in the molecule. We count from along here. It's between carbon 2 and carbon 3. And so you're going to end up with a name there where you're going to have 2, and you separate numbers by a comma, and you separate numbers from letters with a dash, and you've got a methyl group on number 2, haven't you, there? And another methyl group on number 2 there. You've got 2 methyl groups, so you'd say, well, you've got methyl, you've got 2 of them, that's dimethyl. And then you use the stem and the suffix that we found up there. It's methyl on 2, methyl on 3, it's 2,3-dimethyl, the stem is bute, and you've got the suffix is 2-ene. So it's 2,3-dimethyl, bute 2-ene is your name. You worked it out like that. Now, when this reacts with, and this is, you've got to watch here, cold dilute oxidizing agent, because you're going to compare it in a moment with a hot concentrated oxidizing agent. So this is mildly oxidizing, and what happens is that you end up with an alcohol group there and an alcohol group there. And if you drew the skeletal formula for that, you end up with the alcohol group there, the alcohol group there. That and that are those carbons there and there, and you've got 2 methyl groups. There they are, 1, 2, and the other 2 over there. So that's your skeletal formula when you've just got cold dilute oxidizing agent. And you have to compare that with the kind of reaction you get when you get a hot concentrated oxidizing agent. And in that case, the hot concentrated oxidizing agent is sufficient to actually break that double bond and give you a ketone from each side of that double bond. So if you split it there, you're going to end up with that ketone. And yet from the other side, you're going to end up with that ketone. And look at them carefully, they're just exactly the same. So, and then you've got to name that organic compound. Well, what's the longest chain? Well, it's got 3 carbons in a chain, so our stem is going to be prop. The functional group that we're interested in is a ketone, and so the suffix there is -one, and that functional group is on the second carbon. So the answer to that is propan 2O. Okay, good. Scrolling. Okay, so we've got a question here about forming the addition polymer. The easiest way to think about these is if you just had a very simple addition between ethene, then if you had 2 ethene monomers, then that just ends up like this. And if you have a group there, then you end up with a group there and a group there. But we're asking for 3 repeat units of this up here. So let me just try and rub all that out. No. Take that out. We're looking up, let me put the pen back. We're looking for that. And we've got a methyl group, methyl group, methyl group, methyl group. And we're going to have, there it is. And we're going to have 3 of those. So you've got, that's one of them. That's the second. That's the third. And each of these has methyl groups on them like that. Okay, I could keep drawing those in, couldn't I? And that, of course, continues as a polymer chain, and we're just looking for 3 repeat units, and you can label them up like that. Okay, next one. Again, we're being forced to look at names again here. So we've got this, if we just look at the displayed formula here. Okay, we're looking for the longest carbon chain to give us the stem. Well, that's 1, 2, 3. So the stem is going to be prop, and the suffix, because we've got a double bond here, is going to be -ene. And if that's the longest chain there, then we've got a methyl group on the second atom, haven't we, in the chain. So you've got 2, and we separate the number from the words with a hyphen. We've got 2 methyl, and then we've got prop 1 in there. Actually, we should start numbering from here, shouldn't we? 1, 2, 3. 2 methyl, prop 1 in. Okay, next one. We're showing a reaction here where there's a double bond and a hydrogen halide, and you've got to fill in all the parts of the mechanism. And you need to know that when the hydrogen halide approaches this area of high electron density here, then you get a transient dipole in addition to the permanent dipole actually that you have on the hydrogen halide. So you've got slightly positive there, a slightly negative here, and that means you can get a pair of electrons moving there and a pair of electrons moving there. And so you end up with this. Okay. And because the pair of electrons went from the double bond to here, then you've got positive charge there, and actually we've done that wrong. We've now got 3 hydrogens here. We could actually draw those out, it's a bit clearer. Okay, and just to make that absolutely clear, because my drawing's not particularly great here, we've got a positive charge there. Now, and you can see here that's correct, because in the last step of the reaction, you've got a lone pair of electrons on the bromide ion. It's going to form a bond there and gives us this organic compound here, 2-bromo-methyl-propane. And you've got to explain why it is that you get that particular compound forming as the major product in this reaction. Because if you look at this, it didn't have to be this way. It could have been that the positive charge ended up over here rather than here. And so there's a difference in the 2 reaction pathways within our mechanism. So the major pathway is that we had a tertiary carbocation. You can see there the tertiary carbocation has 3 different methyl groups around it. And if the positive charge was over here, that's the minor product, and that would be a primary carbocation. And you've got to say, well, okay, we ended up with the major product, not the minor product, and there's a reason for that. And that is that the tertiary carbocation is stabilized compared to the primary carbocation. And why is it stabilized? Well, you've got a positive charge on the carbon there, and each of these methyl groups is electron releasing. So you can draw little arrows on there. So there's you'd say that has a positive inductive effect, and that means electrons are being released from the methyl groups onto the carbocation from 3 methyl groups for the tertiary carbocation. If it was the primary carbocation, you'd only get a positive inductive effect from 1. And so for that reason, the positive charge density on the carbocation is less. And that's why the tertiary carbocation is more stable than the primary carbocation, because the positive charge density of the carbocation has been reduced because of the positive inductive effect of the methyl groups that surround it. And so that's a pretty good explanation. You're looking for 3 marks here of why you get 1 major product and 1 minor product. We've got our 3 marks there. Good, moving on. Okay, we're looking at, I suppose, organic synthesis now. We've got some reactions here. We've got to draw a skeletal formula. These are our structural formulas. We had displayed formulas earlier on. A skeletal formula for this, well, if the displayed formula would be that. You've got 3 carbons in a chain, an alcohol group at the end. Well, the skeletal formula is 1, 2, 3 carbon atoms and the alcohol group on the end. So that's if you had difficulty with that, you could just draw out the displayed formula here and then figure out, well, this is the skeletal formula. Okay, so we've got to figure out the conditions. We're going from an alcohol to, up here, we're going from an alcohol to a carboxylic acid. That's an oxidation. And so we're going to have a good oxidizing agent. You can use acidified potassium dichromate. But what you're wanting to do is you're wanting to make sure that you convert the alcohol completely to the carboxylic acid. Let's just go down to the one that's following on from this to help us with that. In reaction 2, which you're going from the alcohol to an aldehyde. Now, an aldehyde, if you kept working with it, with the oxidizing agent, would eventually become the carboxylic acid. So with the aldehyde, to prevent it becoming a carboxylic acid, you've got to not only oxidize it, so that these are the same conditions, same reactants, but with the aldehyde, you want to remove it as soon as it forms. But with the carboxylic acid, we want to keep reacting it until all alcohol and any intermediate aldehyde is converted. So the conditions here where you've got the oxidizing agent and we're going to heat it under reflux. So everything just stays in the reaction vessel until we've got the acid that we want. But here, we don't want to do the second step to get the acid. We want to get the aldehyde just as soon as it's formed. We want to get it out of the reaction vessel rather than leave it in there and get it converted to the carboxylic acid. So the difference between them is that here we heat under reflux, but here we heat and we distill. And that means we're going to remove the aldehyde as soon as it forms. And finally, we've got to look at reaction number 3, if I can scroll back up. You're looking at the reaction between an acid, a carboxylic acid, and an alcohol. And that's actually just a pretty good GCSE knowledge. Carboxylic acid and an alcohol makes an ester. And because you had propanol and you had propanoic acid, the ester you're going to make is propyl propanoate. Okay, carboxylic acid and an alcohol makes an ester. We had propanol and propanoic acid makes propyl propanoate. All right, so that was a 1.5 hour paper. We've rushed through it, but I got all the answers discussed there. And if there's things you want to follow up on, then
Okay, so welcome. I'm just going to check that this is working and then we will get started. So are we actually live? That's the question. I'm not entirely sure that the answer is yes at the minute. Right. Okay, so are we live? That's the question. Let's stop and see. All right, welcome. We are trying again. Let's see if this is working. Okay. Okay. We still don't have a second stream. How would one tell whether one were in fact streaming? That's the question. I don't know what that means. Right. Live streaming. I don't. All right. OBS claims that I am live. I am uncertain as to whether I believe it. That's the question here. All right. Take several. Let's see if this works, I guess. Okay, so I don't think I'm live. I'm reasonably sure I'm not live on YouTube. Probably. Let's see. Okay, I'm going to...
I'll be on the Slack channel, and we can raise some questions and work through any questions that you have on the Slack channel. So thanks for listening, thanks for watching, and I'll see you on Slack.